Questions about anything? Last time or anything? So at the end of the hour, I got kind of rushed demonstrating Parseval's identity. There it is down there in the bottom right corner. That's at if I have a continuous function on minus pi to pi, then better than Bessel's inequality is that we get an equality. And so that norm of f squared is the integral of the absolute value of f squared over the interval from minus pi to pi. So that thing on the left is just shorthand for that integral. And the thing on the right is the sum of the squares of that's the complex Fourier coefficients for f. Those are going to lead to a bunch of really fascinating identities. For example, that's the easiest way to figure out that when you sum up 1 over n squared, you get pi squared over 6. We're going to do that. It's fun. Anyway, at the end I was explaining the whole thing. This inequality, 0 less than or equal to that thing, less than or equal to the generic one, that was what came out in Bessel's, the proof of Bessel's, that the Fourier series trigonometric polynomial of order n is the best L2 approximation to the function among such functions. Okay, and the way I got that inequality the day I did this, it was very important that those functions be orthogonal and normalized. To make those functions normalized, all you have to do is divide them by the square root of 2 pi. So that's where the 2 pi comes from in that sum. Anyway, that calculation that day, the fact that all of these things were orthogonal meant when I squared that mess and integrated, a lot of the terms went away. And what's left is exactly the stuff in red there when you use orthogonality and the fact that those things have been normalized. So if you forgot about that, you can go back and look at that day where I demonstrated Bessel's inequality. It was a lot, a couple pages of writing to write out all those integrals, but in the end, they simplified and were clean and nice like that. And of course, that thing being an integral of a square is greater than or equal to 0. And that's the best L2 approximation. So when I take any other one, in fact, in particular, I can take any of those fair polynomials. I can take the fair version of those sums. I would have to collect what all those coefficients are when I add them together. That was the average of all the CNs up to order n. Anyway, I get a sum when I combine them all that looks like the same thing except with ANs where the CNs would have been. And the fact is, Thayer's theorem said, give me a continuous function on minus pi to pi. Let's see, it had to be continuous and 2 pi periodic. Then Thayer's theorem said I could approximate that as close as I want. So in particular, if that continuous function is close to this Thayer polynomial, then its integral would be as small as I want. If I made it less than epsilon over square root of 2 pi, I can make that integral be small. So I can make it less than epsilon using Thayer's, which shows me that thing in between can be made. Let's see, if I have a big enough n, I can make that as small as I want. Okay? And that's exactly what it means for the limit of that sum to be equal to the norm of f squared. Now, give me any epsilon, I can choose un and make that as small as I want. It's between 0 and epsilon, so of course it's going to 0. as n goes to infinity. Any questions about that? That's how the combination of Bessel's and Fayer's gives me the Parseval identity, which is a very nice thing and quite useful. So here's an interesting thing to think about. Bessel's holds if you go back and look at that argument, you realize all I need are integrable functions, really. And so Bessel's holds when f is continuous with finitely many jumps. On minus pi to pi. So does Parseval's hold? In this case, maybe it does. We have to think about it. The answer is yes, because of this little trick. Okay, let me draw. This is going to be a picture proof because I don't want to get bogged down in gory details. But the trick is very simple. Here's the trick. Let's say I've got a thing that has a jump. I'll just have one jump to begin with. That's all. If I can do it for one jump, I can do it for any number of jumps. So let's see. I've got a function with a jump. So it's continuous. And right here, it jumps. And, okay, so that's the red function. That's my f of x. Here's pi, goes over to minus pi. I guess I should make it hook up. If it's going to hook up, I didn't have to do that. It looks like it should hook up by going right about there. Okay, so I want to get a continuous function that makes the integral small. Okay, it obviously can't be. I can't make it continuous and stay close to f all the way because of the stupid jump, but I can make it the integral small, and the trick is I could take a function. I'll make it a little bit less than this thing. It sticks to the curve until I get close to the jump, and then I nosedive down, and then I stick to the curve the rest of the way. I guess to hook it up, I better go and hook it up here. Okay, so the fascinating thing is the L2 norm of the red curve, which is f of x, minus the green curve, squared. Let's see, that would be equal to the integral from minus pi to pi of red minus green squared, which notice that's small on most of the interval. And in the where it does the jumping business, takes that nosedive, well, it's bounded by something, at least, on an interval that I can make as small as I want. So if I were going to graph it, let's see, what would that be? I'd have something that's small, and here it gets kind of big. Let's see, maybe. Let's see, it's going to have a jump, isn't it? What is that? Red minus green is small. It gets big. It actually looks kind of like that. Oh, I'm taking squares, so it's going to be positive. Oh, yeah, so what is it going to do? It's not going to do that. It's going to look more like this. Right? Anyway, the big deal here is I could make this be, this big hump here would go from what's this spot? Let's call this spot something. A. I could make this by making that, I could make this little distance here A plus or minus epsilon. And then I would get an area. This area is really small. It's kind of like the good kernel thing. But in this thing, well, it gets bigger there for a while. But I could make that interval really small, and I could make this peak here be less than or equal to some m. And the m is sort of the jump size. Anyway, we see that area is small. Area can be made small. As small as desired. And so I would get Parsifal's identity for the curve, the green curve, because it's continuous. And then I'd realize, oh, I can get it for the red curve by doing this trick. Anyway, the conclusion, when you think about it, is that Parsifal's holds for piecewise continuous f. You can have finitely many jumps. I don't want to get bogged down in the details, but it's not hard. Piecewise continuous. In particular, the endpoints don't have to hook up. So that's nice to know. So Parsifal's would hold for general f, and you don't have to worry about the endpoints hooking up. In particular, non-2 pi periodic functions. So, in particular, the endpoints at plus and minus pi don't have to hook up. Connect. Okay, any questions about that? Yeah.
Actually construct G, it would just be F until a certain region around this.
Oh yeah, you're right. I could have made it. If I had done that, you wouldn't see that. You wouldn't see it. There'd be green and red covering each other. Right. I could have hung with the curve and then took that nosedive and then hung with the curve again. In fact, that would be smarter, because then I'd have absolute zero outside this little interval where it's bounded by something, but that's a small interval and as small as I want to make it. Yeah, question? Yeah, I could do this with finitely many jumps. I'd get a bunch of little epsilon. Well, I wouldn't. I don't want to think about that. But that's the kind of thing when you get into the perversion of real analysis, you do that kind of thing all the time. All right. I do complex analysis, and complex differentiable functions are incredibly nice. It doesn't have the pathology. But in real analysis, boy, you can come up with some really wild things and examples that blow your mind. In fact, a lot of those examples originated in the study of Fourier series. When you think, oh, how bad could it be? It turns out it can be pretty bad. By the way, this is also, so you see what this means. The fact that L2 integral is going to 0 there, that means that the Fourier series is converging to f and L in the sense of L2. That norm of f minus its actual Fourier series is going to 0. Okay, so if you think of that as a distance between f and its Fourier series, that distance is going to 0. And that's the amazing thing that starts happening when you think of functions as points in a space. So a big fact that falls out from this, big fact, the Fourier series for f converges to f in the L2 sense. And this, I mentioned previously that this is where the Riemann integral was found to be lacking. Because, so Riemann integration has limitations. Because I can come up with Riemann integrable functions that converge in L2 to some that converge in L, or let's see, I can has limitations. There exists Riemann integrable functions Fn that are a Cauchy sequence. In L2 from minus pi to pi, it's the space of square integrable functions that are a Cauchy sequence that don't converge to an Riemann integrable function. It's rather easy to come up with such things. And so, in fact, Lebesgue invented Lebesgue integration to deal with this thing. And then the space of those L2 becomes complete. You give me your Lebesgue integrable functions in L2. If they form a Cauchy sequence in the L2 norm, they converge to something in L2. So that's why Henri Lebesgue figured this out. We're not going to do the Lebesgue integral in this course, but we can study a lot of things with the Riemann integral. It's just that if we wanted to get fancy and discuss Hilbert space and the meaning of L2 convergence, we'd be sunk with the Riemann integral. So what I've shown you is that they do converge in L2, but there's subtle problems that arise when you start trying to take L2 limits of Riemann integrable functions. You get out of the space that way. Okay. Well, I'm going to shift gears now and do something totally different. The topic of today is the Dirichlet problem, and I'm going to do it on the disk. Stein has already done it. I kind of skipped over that section. So now it's time to do it. So the Dirichlet problem on a disk is, I've got the unit disk. I want to find a function that solves the steady state heat problem on the disk with the temperature given on the boundary. Okay, so this is going to be, I'll call this D1 of 0 for the unit disk. That's the set of xy such that x squared plus y squared is less than 1. So that's the inside of the unit disk. Or if you want to say distance, it's the square root of that. And it's going to be convenient to work in polar coordinates. So I'll take an r and a theta in polar coordinates to describe points in there. Okay, and here in the problem, we know the temperature on the boundary. On the unit circle. Let's call that C10. That's the spot, the green stuff. That's the green circle. Okay. Let's call the temperature. That's it. And we've allowed it to, so the temperature on the unit circle, which is held, it's steady. So we know the temperature on the unit circle, which is, we have refrigerators and heaters, and we're keeping it at exactly that temperature. So the temperature on the circle is held steady. So think about this room. We make this wall 100 degrees and that wall 50 degrees. And then we wait for the temperature in the room to sort of spread around and equalize. Temperature does that. It's a diffusion process. And so, of course, if it's 100 there and 50 there, then in the middle, it's going to be the midpoint, etc. But anyway, we wait until it stabilizes. So let the temperature reach steady state. The real heat problem, that would take forever. You would never reach steady state. But what happens is it's an exponential thing. It's like e to the minus something speed. It zooms into almost a steady state, in almost the limiting steady state temperature pretty quickly, in fact. And so studying steady state is a reasonable thing to do. If you wait 20 minutes, this room will reach, it's so close to its steady state, you wouldn't notice the difference. Okay, so steady state, so the heat problem, we talked about the wave equation. The heat equation is du dt equals a c squared times the Laplacian of u. Okay, if it's reached steady state, then this derivative would be 0. Because it's no longer changing. And so solutions to the heat problem are harmonic. Solutions to the steady state heat problem are harmonic functions. Now that means that their Laplacian is 0. Meaning that d2 by dx squared plus d2 by dy squared u is identically 0. This is the Laplace operator, and this is the Laplace equation. So Laplacian u is identically 0. That's the Laplace equation. That's the definition of harmonic function. And so the Dirichlet problem is we're looking for a solution to this problem. So 1, we need a Laplacian of u to be 0 in the inside the disk. 2, we need it u to be continuous up to the circle. So it has boundary values, continuous up to the green circle. And 3, in polar coordinates, I would have u of 1 theta is a given function. So this would be the temperature on the circle. This is a given function. And of course it would be continuous, and not only that, so this is going to be for 0 is less than or equal to theta is less than or equal to 2 pi, and let's see, and note, we're assuming that this function is continuous on the boundary, so we would need that f of 0 and f of 2 pi has to hook up. So f is continuous on the boundary. Okay. And I'm going to assume we want for convenience, we'll want f to be more than continuous. We'll want it to be C1 smooth, which we'll also want the derivatives to hook up. So another thing to note, for the derivatives, for f to be, so here's a remark, for f to be C1 smooth on the circle, we need the derivatives to hook up too. Otherwise there'll be a kink. Okay, so an interesting thing, a fact that Math 261 fact, you learned how to do the change of variables formula, And so the Laplacian of u is d2u dx squared. When you do it in polar coordinates, you get d2u dr squared with respect to the radius, and 1 over r du dr, and 1 over r squared d2u d theta. That is the Laplacian in polar coordinates. It's a typical exercise. And if you're in the engineering classes, you use the Laplacian in polar coordinates all the time whenever you do something that has radial symmetry, and when you're studying potentials and et cetera, et cetera. Okay. Well, we're going to try to solve this problem using Johann Bernoulli's brilliant idea of separation of variables. Let's try. It's a PDE, and so we have to resort to drastic measures. Separation of variables. We're going to look for a u. So in polar coordinates it would be a u of r theta, and I'll have a capital R of r function. So a function of, here's a capital theta. You don't see this very often. That's a capital theta. R of r times theta of theta. Functions of r and theta alone. Okay, we want the Laplacian to be 0. So let's calculate the Laplacian in polar coordinates. There's the Laplacian in polar coordinates when I pile r derivatives on. So in the red stuff underlined there. The derivative with respect to r would give me an r double prime. And the theta function would just sit there when I calculate that first term. And then I would get 1 over r times r prime. Du to r would be r prime, and the theta function would just sit there. And then finally, I'd get 1 over r squared. These derivatives would hit the theta function. So r would just sit there, and I'd get a theta double prime. And I'd want that to be identically 0. And back when we did the vibrating string problem, we pulled all the r functions to one side and all the theta functions to the other side. And when you think about how to do that, well, you have to stare at this for a while. I can do that if I divide the whole mess by r times theta, divide by r theta, and then also multiply by r squared. And when you do that, on this side you'll get r squared, r double prime, plus r times r over r. And you get another term which you can stick on the other side, and that's minus theta double prime over theta. And like we did in the vibrating string problem, a function of r being equal to a function of theta means that they both have to be constant. And so we'll call those two things the same constant, lambda. Remember, to see that, I could let theta be pi over 2 and just stick it in there and realize, oh, the thing on the left is constant. And once I know the thing on the left is constant, then I can let theta move again and see that they're both a constant and the same constant. So that's how we saw that. So that's what has to be true if we're going to find a solution in this form. So I would say let little theta equal pi over 2, etc. Okay, we get two ODEs. Interesting one. I told you didn't have to know much about ODEs, but this is going to feel like kind of like when we had the. We'll have the same old ODE in the theta problem. So let's see. The theta problem is going to be theta double prime plus lambda theta equals 0. That's an easy one. That's simple harmonic motion. And, well, that's when lambda is positive. When lambda is negative, it's related to spring problems. Let's see, no. The spring problems are when lambda is positive. But we're going to have to allow lambda to be 0 and negative and think about those cases. What's the other problem? It's when I put it's r squared r double prime plus r times r. This was a prime. Sorry, I dropped a prime. R times r prime minus lambda r equals 0. That's a famous kind of differential equation called an Euler equation. One of my favorite math jokes is that if mathematicians had to name all the animals in the world, there'd be a cat. There'd be a cat with no legs, that would be a snake. There'd be a cat with a long nose, that would be an elephant. It seems like we name everything we see Euler equation or Euler function or Euler something. And here's another example. That's an Euler equation, and we're going to solve it by Euler's method, which is very simple. Okay, let's first think about the theta problem, because that's going to limit the lambdas. So let's first do the theta, and we already know how to do the theta problem. But let's think about, there's something interesting about the theta problem. We want the things to hook up. So the theta problem is this ODE, lambda double prime plus lambda, theta double prime plus lambda theta equals 0. And we want periodic, these are called periodic boundary conditions. We don't want the function to rip when we come around 2 pi. It's got to connect. And we also don't want a kink there. We would expect these solutions to be nice and smooth. And for that to be the case, we need periodic boundary conditions. We need theta at 0 to be equal to no. Remember, these are defined on the whole circle. So we certainly wouldn't want to rip when it comes around and hooks up. And we also don't want a kink. So we would need phi prime at 0 to be equal to, I keep saying different words for theta. Theta prime of 2 pi. So that means no jumps and no kinks. At the 0-2 pi interface connection. That's what those mean. And that's going to limit the lambdas. Okay, so let's think about lambda equals 0. We did this carefully in the vibrating string problem. I got theta double prime is is equal to 0, and that means that theta of theta is a theta plus b. And of course, let's see, what is no jumps means that the a has to be 0. So let's see, theta of 0 is equal to b. Theta of 2 pi is equal to a times 2 pi plus b. Those are supposed to be equal, and you see that a better be 0. We see that we need a equals 0 for no jump. Okay, so the a has to be 0, but the derivatives hook up then. So we see that we get a solution for once. So phi prime of 0 equals b, and that's also phi prime at 2 pi. So, oh good, we got a solution. We get a possible solution. Solution theta of theta is identically equal to 1. Because I'll be putting constants in when I take linear combinations later. So we get this possible solution of the constant solution 1 when lambda equals 0. Okay, that's going to be nice to know. That means I'll have to solve the Euler equation for lambda is equal to 0, and that's not hard at all. I can just integrate that one at least pretty easily, I think. Okay, I'll write this. Theta for 0 of theta is the function 1.
Why are the derivatives equal to b?
What? Oh, you're right, I'm right. What? That's dumb. You're right. I know that a has to be equal to 0. So that means that theta of theta is equal to b. And you're right, this is a big fat 0. When I take a is equal to 0, the derivative is 0, and they hook up. Sorry about that. And here I'm taking b equal to 1. Because later on, I'll take linear combinations. And that's where the b will come back. Okay, so let's do the next easy case. Let's do the case lambda less than 0. Okay, then remember we get, that's the net exponential case. We get theta of theta equals C1 e to the k theta plus C2 e to the minus k theta. So that was where lambda is equal to minus k squared. And when you play around trying to get the periodic boundary conditions, there's just no way you can do that. Ouch. Can't satisfy the periodic boundary conditions. It's not hard to see that. I just don't want to. It's a plus lambda. Right, so I'm doing the lambda less than 0 case, but can't satisfy the periodic boundary conditions. Checking that, you have to sit down and just do it. It's not hard. So BC, boundary conditions. And so we get no solutions, except the 0 solutions. we get no solutions except the identically zero solutions, which you don't care about. If it's absolute zero, when it starts, it's going to stay absolute zero. Okay, so the lambda equal positive ones, you get periodic solutions, I won't go through the details, but it's not hard. You get periodic solutions exactly when, just like in the string problem, exactly when lambda equal n squared. And then the theta functions, call them theta n of n, theta n of theta equals an cosine n theta, think Fourier series, okay, so now I've got to solve the Euler equation for these various n's. Unfortunately, I'm running out of time. So we need to solve the Euler equation for lambda equals 0, 1 squared, 2 squared, 3 squared, ... So here's Euler's. The case lambda equals 0 will be easy. I can just integrate it basically. Lambda equals 0 will be easy. The lambda equal not 0, we'd have r squared r double prime plus r prime minus lambda r equals 0. Is that my Euler equation? Oh, minus, yeah, that's going to be minus n squared there. And Euler's brilliant, this is the lambda unequal to 0. Euler's brilliant idea, he looked at that and said, well, what kind of functions, when you differentiate them, drops a degree? And it's, so Euler's idea, try r of r equals r to a power, and make it work. That's a really classic thing to do in ODEs. You guess it and make it work, like partial. When you do the method of undetermined coefficients and things like that, it happens again and again. And the reason that's a brilliant idea is when you differentiate r to the p, one derivative would be p times r to the p minus 1. And so that r in front of the derivative would bring it back up to r to the p. Then when you differentiate it again, you'd get p times p minus 1 r to the p minus 2 after two differentiations. And the r squared there would bring that back up to p. And so what you get when you do that and plug it in is basically a quadratic equation times r to the p equals 0. And a quadratic equation has two roots. And so you're going to get two solutions, two p's that make that work. And I'll go through the details on Monday. It's kind of fun and easy. And that's exciting. That means that next time I'm going to have a solution to the heat problem. It's going to involve a linear combination of all the solutions I get by this procedure. Okay.